There is a particle inside you, right now, that can do something no other force carrier in the universe can do. It can reach into the heart of an atom and change what a particle fundamentally is. A neutron becomes a proton. One type of quark transforms into another. Matter itself is rewritten. And the particle responsible for this extraordinary act of transformation is one of the heaviest elementary particles ever confirmed to exist. It is so massive that it cannot survive on its own for more than a trillionth of a second. It appears, it acts, and it is gone, faster than light could cross the width of a single proton. How can something so powerful die so quickly? And if it is truly fundamental, if it is not built from anything smaller, then what exactly is it made of? The answer touches the deepest structure of reality. Before we go any further, if you find this kind of deep dive into the physics of reality interesting, a quick like or subscribe really helps the channel grow. It is a small thing for you, but it makes a huge difference for me. Now, let's begin. You already know that forces exist. You feel gravity every second of your life. It pulls you toward the floor. It holds the moon in orbit around the Earth. It keeps the Earth falling around the sun. You have felt the push of a magnet snapping against your refrigerator door. You have watched lightning tear across a summer sky. You have seen your hair stand on end after rubbing a balloon. These are forces. They reach across space and make things happen. Two objects that are nowhere near each other can somehow push or pull on one another. That fact alone, if you really sit with it, is already strange. How does the Earth know the sun is there? How does a magnet reach out through empty air and grab a piece of iron sitting on a table? For most of human history, nobody had a satisfying answer. Forces were just part of reality, invisible hands that moved the world. But starting in the 20th century, physicists uncovered something astonishing about how forces actually work. Forces are not invisible hands. Forces are carried by particles, real, physical particles that travel between objects and deliver the push or the pull. This idea is one of the most important in all of modern physics. It completely changes what a force is. A force is not a mysterious influence that somehow bridges empty space. A force is an exchange. Two objects interact by throwing particles back and forth between them. The particle doing the throwing and catching is called a force carrier, or a gauge boson. And understanding this idea, truly understanding it, is the first step toward grasping what the W boson is and why it behaves the way it does. Let us start with the force you are most familiar with at the atomic level: electromagnetism. This is the force responsible for light, for radio waves, for the chemical bonds holding the molecules of your body together, for the repulsion between two positive charges and the attraction between a positive and a negative one. Electromagnetism is carried by a single particle, the photon. You already know photons as particles of light. Every beam of sunlight streaming through your window is a flood of photons. Every color you see is your brain interpreting photons of different energies arriving at your retina. But photons do much more than let you see. They are the reason charged particles interact at all. When two electrons repel each other, what is actually happening at the deepest level is that they are exchanging photons. One electron emits a photon, the other electron absorbs it. The exchange transfers momentum between them, pushing them apart. This is not a metaphor. This is the actual physical mechanism by which electromagnetism operates. The framework describing this process is called quantum electrodynamics, and it is one of the most precisely tested theories in the history of science. Its predictions match experiments to better than 10 parts in a billion. That is like predicting the distance from New York to Los Angeles to within the width of a human hair. Now, here is the crucial thing about the photon that makes electromagnetism work the way it does. The photon has no mass. Zero. It is completely massless. This single fact determines almost everything about how electromagnetism behaves. Because the photon is massless, it can travel at the speed of light. In fact, it must travel at the speed of light. It cannot go slower. It cannot stop. From the moment it is created to the moment it is absorbed, it moves at exactly 299,792 kilometers per second. No faster, no slower. And because the photon is massless, it can be created with arbitrarily little energy. You can have a photon with a tiny amount of energy, a long, lazy radio wave stretching across kilometers, or a photon with enormous energy, a gamma ray with a wavelength smaller than an atom. There is no minimum price you must pay to produce one. This has a direct and profound consequence. The electromagnetic force has infinite range. Two charged particles can interact across any distance, no matter how far apart they are. The force weakens with distance, yes. It follows an inverse square law, dropping off as you move farther away. But it never truly reaches zero. A proton on one side of the observable universe can, in principle, exert an electromagnetic influence on an electron on the other side. The influence would be unimaginably faint, vanishingly small, but it would not be zero. This infinite range is a direct consequence of the photon being massless. No mass means no minimum energy cost, means the force can reach out forever. Now hold all of that in your mind. The photon is massless. It travels at the speed of light. It has no electric charge. It can exist for an indefinite amount of time, and it gives electromagnetism an infinite range. Remember these properties, because what comes next is going to feel like stepping into a different universe. There is another force in nature. It does not hold atoms together. It does not create light. It does not make magnets stick to your refrigerator. Most people have never heard of it by name, even though it is happening inside your body right now, inside every star in the sky, inside every atom that has ever undergone a certain kind of transformation. This force is called the weak interaction, and it has its own carrier particles. One of them is the W boson, and the W boson is almost nothing like the photon. The W boson is not massless. It is extraordinarily, almost absurdly massive. Its mass is approximately 80.4 gigaelectron volts divided by c squared. If that unit does not mean much to you, here is a comparison that should stop you in your tracks. A proton, the positively charged particle at the core of every atom, has a mass of about 0.938 gigaelectron volts divided by c squared. The W boson is roughly 86 times heavier than a proton. Think about what that means. A single W boson is heavier than an entire atom of iron. Iron has 26 protons and about 30 neutrons in its nucleus. Add up all that nuclear mass, and the W boson still outweighs it. This is not a small particle carrying a subtle influence. This is a colossus. One of the heaviest elementary particles ever directly detected, and yet it is classified as a force carrier. It is supposed to do the same kind of job the photon does, mediating interactions between other particles. But it does that job in a radically different way because of that enormous mass. The photon is electrically neutral. It carries no charge. It can mediate the electromagnetic force without altering the identity of the particles involved. An electron that emits a photon is still an electron afterward. A proton that absorbs a photon is still a proton. The photon transfers energy and momentum, but it does not change what anything is. The W boson does not have this luxury. The W boson is electrically charged. It comes in two versions. The W plus carries a positive charge, and the W minus carries a negative charge. Each one carries exactly 1 unit of electric charge, the same magnitude of charge carried by a proton or an electron. This is deeply unusual. Among the force carriers of the Standard Model, only the W boson carries electric charge. The photon is neutral. The gluon, which carries the strong force between quarks, carries a type of charge called color charge, but not electric charge. The Z boson, the W boson's close relative, is electrically neutral. Only the W+ and W- carry the familiar electric charge you learned about in school. And that charge is not decorative. It is functional. It is the reason the W boson can do something no other force carrier in nature can do. But we will get to that transformation in detail later. For now, understand that the W boson is charged, heavy, and very different from the photon. Because the W boson is so massive, creating one requires an enormous amount of energy. You cannot produce a W boson cheaply. The energy cost is dictated by Einstein's most famous relationship, E = mc². Mass and energy are two expressions of the same thing. To create a particle with the mass of the W boson, you need at least 80.4 gigaelectronvolts of energy concentrated in one interaction. That is an enormous amount by subatomic standards. For comparison, the energy involved in a typical chemical reaction, the kind that powers your metabolism or lights a match, is on the order of a few electron volts. The W boson requires roughly 80 billion times more energy than a single chemical bond provides. This is why you do not encounter free W bosons floating around in your living room. Nature does not casually produce them. They appear only in extremely energetic processes, deep inside atomic nuclei during certain kinds of radioactive decay, in the hearts of stars during the fusion reactions that generate light, or in the violent collisions inside particle accelerators where protons are smashed together at velocities approaching the speed of light. And here is where the strangeness deepens. Even when a W boson is produced, it does not last. It cannot last. Its lifetime is approximately 3 times 10 to the power of -25 seconds. Let me try to make you feel how short that is. Light is the fastest thing in the universe. In 1 second, light travels about 300,000 kilometers. That is far enough to circle the Earth roughly 7.5 times. In 3 times 10 to the -25 seconds, light travels barely 1/20th of the diameter of a proton. The W boson is born, it acts, and it is gone before a beam of light could cross a distance smaller than any atomic nucleus ever measured. It exists for such an unimaginably brief flicker that no detector on Earth can observe it directly. We know it exists because of what it leaves behind. We see the products of its decay, the electron and the neutrino, or the quark and the antiquark that it breaks apart into after its fleeting moment of existence. We reconstruct its presence from the debris, the way you might reconstruct a firecracker from the scorch marks and scattered paper after the bang. Now compare this to the photon. A photon can travel across the entire observable universe. Light from distant galaxies has been traveling for more than 13 billion years and is still going. A photon emitted during the first few 100,000 years after the Big Bang is still reaching our telescopes today as the cosmic microwave background radiation. The photon is eternal in the sense that it does not decay on its own. Left alone in empty space, a photon will travel forever. The W boson, by contrast, cannot survive long enough for light to cross a fraction of a proton. The difference in lifetimes between these two force carriers is not a matter of degree. It is a difference so vast that the word contrast barely begins to capture it. One particle lives forever and reaches across the cosmos. The other appears and vanishes in a time interval so short that human language does not have a word for it. This difference in lifetime is not a coincidence. It is not an accident of nature. It is a direct and unavoidable consequence of mass. The photon lives forever because it is massless. The W boson dies almost instantly because it is enormously heavy. These two facts are connected by the deepest rules of quantum mechanics, and understanding that connection is at the heart of this entire story. But let us save the full explanation of why mass causes rapid death for later. Right now, what matters is that you see the contrast clearly. The electromagnetic force has a massless carrier and an infinite range. The weak interaction has a massive carrier and an almost absurdly short range. The weak force operates only across distances smaller than the width of a proton. Beyond that range, it effectively vanishes. Two particles separated by more than about 10 to the negative 18 meters will not feel the weak force at all. That distance is roughly 1,000th the size of a proton. The weak interaction is confined to a volume so tiny that it makes atomic nuclei look like open prairies. This is why the weak interaction was the last of the fundamental forces to be understood. Gravity was described by Isaac Newton in the 17th century and refined by Einstein in the early 20th. Electromagnetism was unified by James Clerk Maxwell in the 1860s. The strong force binding quarks inside protons and neutrons was described by quantum chromodynamics in the 1970s. But the weak interaction, because it operates at such absurdly tiny distances and involves such elusive particles, took longer to pin down. The theoretical framework for the weak force was developed in the 1960s and 70s by Sheldon Glashow, Abdus Sulam, and Steven Weinberg. Their work showed something remarkable. The weak force and electromagnetism, despite looking completely different at the energies we experience in daily life, are actually two aspects of a single unified force called the electro-weak interaction. At very high energies, the kind of energies that existed in the first moments after the Big Bang, the electromagnetic force and the weak force are indistinguishable. They behave as one force carried by four massless particles. But as the universe cooled, something happened that broke this symmetry. Three of those four carriers acquired enormous mass, while one remained massless. The massless one became the photon. The three massive ones became the W+, the W-, and the Z boson. The force that was once unified split into two forces with very different properties. Electromagnetism with its infinite range and the weak interaction confined to subatomic distances. That symmetry breaking, the event that gave the W and Z bosons their mass while leaving the photon untouched, is one of the most important events in the history of the universe. It shaped the laws of physics as we know them. It determined the range of forces, the stability of particles, and ultimately the kind of matter that could exist. And at the center of that event is another particle you may have heard of, the Higgs boson, and the field associated with it. But we will explore that connection in full when we get to the question of why the W boson is so heavy. For now, let us step back and make sure the picture is clear. You live in a universe with four known fundamental forces. Gravity holds planets in orbit and galaxies together. Electromagnetism governs light, chemistry, and the structure of atoms. The strong force binds quarks into protons and neutrons and holds atomic nuclei together. And the weak interaction, quietly and almost invisibly, operates inside those nuclei to transform one type of particle into another. Each of the three non-gravitational forces has its own carrier particles. Electromagnetism has the photon. The strong force has 8 types of gluons. The weak force has 3 carriers, the W+, the W-, and the Z boson. The W bosons are charged, the Z boson is neutral. All 3 are massive. And that mass is what makes the weak force so fundamentally different from electromagnetism, even though the two forces are secretly related. The W boson is the particle that makes the weak force weak. Not weak in the sense that it does unimportant things. The weak force is responsible for the nuclear reactions that power the sun. It drives certain types of radioactive decay. It played a critical role in determining the balance of matter and antimatter in the early universe. It is essential to the existence of the elements heavier than hydrogen. Without the weak force, and without the W boson carrying it, the universe as you know it would not exist. The W boson is weak only in the sense that its massive weight confines it to an incredibly short range. It cannot reach very far. It cannot linger very long. But within its tiny domain, it does something no other force carrier can do. Something that changes the identity of matter itself. The W boson was not just predicted, it was found. In 1983, experiments at CERN, the European Organization for Nuclear Research, directly detected the W boson for the first time. The experiments were conducted at the superproton synchrotron, a particle accelerator that collided protons with antiprotons at energies high enough to produce W bosons from the collision energy. The discovery was led by Carlo Rubbia and the UA1 collaboration, with critical contributions from Simon van der Meer, whose technique for cooling and focusing the antiproton beam made the experiment possible. Both men were awarded the Nobel Prize in Physics in 1984. The mass they measured was consistent with the predictions of the electroweak theory. The W boson was real, it was heavy, and it decayed so fast that it could never be seen directly, only inferred from its decay products. That discovery confirmed a picture of reality that is both elegant and deeply strange. The forces shaping the matter inside every atom of your body are not abstract influences. They are carried by real particles. And one of those particles, the W boson, is a charged, massive, breathtakingly short-lived entity that appears from the energy of an interaction, changes the very nature of the particles it touches, and then disintegrates before light could cross a distance smaller than anything you have ever seen or imagined. It is a particle that lives on borrowed energy and borrowed time, and the debt comes due almost before the loan is made. Everything we explore from this point forward builds on this foundation. You now know that forces are carried by particles. You know that the photon carries electromagnetism, and that the photon's lack of mass gives that force infinite range and eternal carriers. You know that the W boson carries the weak interaction, and that its enormous mass confines it to subatomic distances and destroys it almost the instant it appears. You know that the weak force and electromagnetism were once a single force, and that something in the early universe broke the symmetry between them, giving mass to the W and Z bosons while leaving the photon massless. And you know that the W boson was directly discovered in 1983 at CERN, confirming one of the most profound predictions in the history of particle physics. What you do not yet know is what the W boson actually does when it appears inside matter. You do not yet know why its mass forces it to die so quickly, and you do not yet know the answer to the deepest question in the title of this story. If the W boson is not made of quarks, not built from smaller pieces, not composed of anything at all, then what is it? These questions have answers, and those answers will take us into the heart of the standard model of particle physics, into the quantum fields that permeate all of space, and into a vision of reality that is stranger and more beautiful than anything you might expect. Every other force in nature leaves particles alone. Gravity pulls a planet toward a star, but the planet is still a planet when it arrives. Electromagnetism pushes two electrons apart, but both electrons remain electrons. The strong force grips quarks together inside a proton, but it does not change what kind of quarks they are. These forces move things. They accelerate things. They bind things together or push them apart, but they do not alter the fundamental identity of the particles they act upon. The W boson does something different. The W boson reaches into a particle and rewrites what it is. A quark of one type goes in, a quark of a completely different type comes out. A neutron becomes a proton becomes a neutron. One variety of matter transforms into another variety of matter right there, inside the nucleus of an atom, in a space smaller than anything you could ever see. This ability to change the identity of fundamental particles is unique in all of known physics. No other force carrier can do it, and it is the single most important thing the W boson does. Without this ability, the universe would be a profoundly different and far emptier place. To understand how this transformation works, you need to know a little about what protons and neutrons actually are. You were probably taught in school that atoms have a nucleus made of protons and neutrons, with electrons orbiting around the outside. That picture is correct as far as it goes. But protons and neutrons are not elementary. They are not the bottom of the ladder. Each proton is made of 3 quarks. 2 of them are called up quarks, and 1 is called a down quark. Each neutron is also made of 3 quarks, but in a different combination. A neutron has 1 up quark and 2 down quarks. That is the only structural difference between a proton and a neutron. Swap 1 down quark for an up quark, and a neutron becomes a proton. Swap 1 up quark for a down quark, and a proton becomes a neutron. The difference between these two particles, the 2 building blocks of every atomic nucleus in the universe, comes down to the identity of a single quark. Up quarks and down quarks are the 2 lightest members of a family of 6 quarks. Physicists call the different types of quarks flavors, which is just a whimsical label for a very real physical property. The 6 flavors are up, down, strange, charm, bottom, and top. They range enormously in mass. The up quark is the lightest, with a mass of only about 2.2 megaelectronvolts divided by c². The top quark is the heaviest, weighing in at about 173 gigaelectronvolts divided by c², roughly as heavy as an entire atom of gold. Despite this enormous range, all 6 flavors of quark interact through the strong force and the electromagnetic force in essentially the same way. What makes them different is their mass, their electric charge, and critically, how they behave under the weak interaction. Because the weak interaction, through the W boson, is the only force that can change one flavor of quark into another. Here is how it works in the most common and most important example. Consider a neutron sitting inside an atomic nucleus. The neutron is made of 1 up quark and 2 down quarks, bound together by the strong force carried by gluons. Now imagine that one of those down quarks does something. It emits a W- boson. The moment it does this, it is no longer a down quark. It has become an up quark. The electric charge is conserved in this process. A down quark has an electric charge of -1/3. An up quark has an electric charge of +2/3. The difference is exactly 1 unit of negative charge, which is carried away by the W- boson. So the bookkeeping works out perfectly. The quark changed its identity, and the W boson carried away the difference in charge. Now look at what has happened to the neutron. It started with 1 up quark and 2 down quarks. One of those down quarks has become an up quark. So the neutron now contains 2 up quarks and 1 down quark. That is the definition of a proton. The neutron has become a proton. The particle has changed its fundamental identity without anything being added from outside. The transformation happened from within, mediated by the emission of a W boson. But the story does not end there. The W- boson that was emitted now exists as a free particle. And as we established earlier, it cannot last. It is far too massive to survive for more than the tiniest imaginable fraction of a second. Almost immediately, the W- decays. It falls apart into lighter particles. In the most common version of this process, the W- decays into an electron and an electron antineutrino. These two particles fly away from the nucleus at high speed, carrying energy and momentum with them. The electron is detectable. You can measure its energy, its direction, its charge. The antineutrino is almost undetectable. It barely interacts with anything. It will fly through the entire Earth without touching a single atom. But it carries away energy and momentum that you can infer from what is missing in the measurements. This entire sequence of events is called beta decay. It is one of the most common forms of radioactive decay in nature. A neutron turns into a proton by emitting a W- boson, which immediately decays into an electron and an antineutrino. The result is that the atom has gained a proton and lost a neutron. Its atomic number has increased by 1, which means it has become a different element. Carbon-14 undergoes beta decay to become nitrogen-14. Tritium, a heavy form of hydrogen with 2 neutrons, undergoes beta decay to become helium-3. Potassium-40, the radioactive isotope found in bananas and in the rocks beneath your feet, undergoes beta decay to become calcium-40. Every time this happens, a W boson is responsible. Every single time. There is no other mechanism. The W boson is the agent of transformation, the particle that physically carries the change from one identity to another. The reverse process also occurs. A proton inside a nucleus can emit a W+ boson, turning into a neutron. When this happens, the W+ boson decays into a positron, which is the antimatter partner of the electron, and an electron neutrino. This is called beta plus decay, or positron emission. It is less common in nature than beta minus decay because it requires energy input, but it happens inside certain unstable nuclei, and it is critically important in medical imaging. Positron emission tomography, the scanning technique used in hospitals around the world, works by detecting the gamma rays produced when the emitted positrons annihilate with electrons in surrounding tissue. Every one of those scans depends on the W boson doing its job inside an unstable nucleus. There is something worth pausing on here: the neutrino. For decades, the neutrino was one of the greatest mysteries in physics. When physicists first studied beta decay in the early 20th century, they noticed a problem. The electron flying out of the decaying nucleus did not always carry the same amount of energy. Sometimes it came out fast, sometimes it came out slow. The total energy before the decay was always the same, but the electron's share varied. Energy seemed to be disappearing. Some physicists, including Niels Bohr, seriously considered the possibility that energy conservation might not hold inside atomic nuclei. But in 1930, the Austrian physicist Wolfgang Pauli proposed a different and far more radical solution. He suggested that an unseen particle was carrying away the missing energy. A particle so light and so weakly interacting that it passed through all detectors without a trace. He called it a neutron at first, but when the actual neutron was discovered in 1932, the Italian physicist Enrico Fermi renamed Pauli's hypothetical particle the neutrino, Italian for little neutral one. For 26 years, the neutrino remained undetected. Many physicists believed it would never be found because it interacted so feebly with matter. But in 1956, Clyde Cowan and Frederick Reinese detected neutrinos for the first time using a nuclear reactor as a source and a massive tank of water as a detector. The neutrino was real, and it interacted with matter only through the weak force, only through the W and Z bosons. Nothing else in nature could touch it. This tells you something important about the W boson's role. The W boson is not just the agent of transformation for quarks. It is the primary connection between neutrinos and the rest of the material world, alongside the Z boson. Without the W and Z bosons, neutrinos would be completely invisible. They would pass through the universe without interacting with anything ever. They would exist, but would have no effect on matter. The weak force carriers are the bridge between neutrinos and everything else. When a neutron undergoes beta decay, the W boson that is emitted creates a neutrino out of pure energy. And when a neutrino occasionally interacts with matter, which is extraordinarily rare but does happen, it does so by exchanging a W or Z boson with a quark or a charged lepton. The W boson is the chief gatekeeper of the neutrino world. But the W boson has another strange property that sets it apart from every other force carrier. A property so unexpected that when it was first proposed, many physicists refused to believe it. The W boson cares about handedness. In physics, handedness refers to the relationship between a particle's spin and its direction of motion. Every particle spins, not like a top spinning on a table, but in a quantum mechanical sense, carrying an intrinsic angular momentum. If you could watch a particle flying toward you and its spin were rotating counterclockwise, physicists would call that left-handed. If the spin were rotating clockwise, it would be right-handed. For most forces, handedness does not matter. Electromagnetism treats left-handed and right-handed particles identically. The strong force does the same. Gravity does not care about handedness. If you built a mirror image version of any electromagnetic or gravitational process, it would behave exactly the same way. The laws of physics, it seemed, were perfectly symmetric between left and right. But in 1956, two theoretical physicists, Sung-Dao Lee and Chen-Ning Yang, proposed that the weak interaction might break this symmetry. They suggested that the weak force might distinguish between left-handed and right-handed particles, that it might violate parity, the principle that the laws of physics look the same in a mirror. The idea was provocative, even disturbing. Symmetry between left and right seemed like such a basic feature of nature that many physicists considered it unthinkable that any force could violate it. But Lee and Yang pointed out that nobody had actually tested parity conservation in weak interactions. Every previous test had involved electromagnetism or the strong force, where parity is conserved. The weak force, being so much harder to study, had simply been assumed to follow the same rule. An assumption is not a fact. The test came quickly. In 1957, the physicist Chi-En Xiong-Wu and her collaborators performed a landmark experiment using cobalt-60 nuclei cooled to near absolute zero in a magnetic field. The magnetic field aligned the nuclear spins so they all pointed in one direction. If parity were conserved, the electrons emitted during beta decay should fly out equally in both directions along the spin axis. There should be no preference. The mirror image experiment would look the same. But that is not what Wu found. The electrons came out preferentially in one direction. The mirror image version of the experiment would look different. Parity was violated. The weak force distinguished between left and right. This result sent a shockwave through physics. It meant the W boson interacts only with left-handed particles and right-handed antiparticles. A left-handed electron can interact with a W boson. A right-handed electron cannot. The W boson literally ignores half the particles it could potentially interact with, based solely on their handedness. No other force does this. The photon does not care about handedness. The gluon does not care. Only the W boson, and by extension the weak interaction, has this preference. It is one of the most profound asymmetries in all of nature, built into the structure of the weak force at the most fundamental level. You live in a universe that is not symmetric between left and right. The W boson is the reason why. Now, I need to make something clear about what is happening during beta decay in terms of the W boson's existence. When I described the down quark emitting a W- boson that then decays into an electron and an antineutrino, I was telling the story in a sequence that makes narrative sense. First the quark changes, then the W boson appears, then the W boson decays. But the reality is more subtle than that. In most cases of beta decay, the W boson never truly exists as a free, independent particle traveling through space. The energy available inside a decaying neutron is only about 1.3 mega-electron volts. The W boson's mass is about 80.4 giga-electron volts. There is nowhere near enough energy to create a real W boson, not even close. The gap is a factor of roughly 60,000. So what is actually happening? The W boson in beta decay is what physicists call a virtual particle. A virtual particle is not a fiction. It is not a mathematical trick. It is a real feature of quantum field theory, but it behaves differently from a particle you could catch in a detector. A virtual W boson does not need to have the mass of a real W boson. It exists as an intermediate state in a quantum process, borrowing energy from the uncertainty principle for a time so short that the energy debt is never called in. The uncertainty principle allows energy to fluctuate by an amount that is inversely proportional to the time interval. For extremely short times, enormous energy fluctuations are permitted. The virtual W boson exists for a time so fantastically brief that nature allows the temporary creation of something far heavier than the available energy would normally permit. But there is a cost. The more massive the virtual particle, the shorter the time it can exist, and the shorter the distance it can travel. This is why the weak force has such a tiny range. The virtual W boson can only travel about 10 to the negative 18 meters before the energy debt comes due. That is roughly 1,000th the diameter of a proton. Beyond that distance, the influence of the W boson vanishes. The weak interaction cannot reach any farther because its carrier is too heavy to travel any farther, even as a virtual particle. When physicists produce real W bosons in particle accelerators, the situation is different. In a high-energy collision at a machine like the Large Hadron Collider, protons smash together with enough energy to create actual, en-masse shell W bosons. These are real particles with the full mass of 80.4 giga-electron volts. They exist as genuine, propagating entities. But even then, they last only about 3 times 10 to the power of negative 25 seconds before decaying. So whether the W boson is virtual or real, its time in this world is vanishingly brief. The virtual version borrows energy it does not have, and exists for a time too short to measure. The real version carries its full mass honestly, but decays almost the instant it is born. Either way, the W boson is a fleeting visitor. It appears just long enough to do its job, and then it is gone. Let me be very precise about what that job is. The W boson changes quark flavor. It is the only particle in the standard model that does this. The photon cannot change a quark's flavor. The gluon cannot change a quark's flavor. Even the Z boson, the W boson's close neutral relative, cannot change a quark's flavor. The Z boson mediates certain weak interaction processes, but these are processes where a particle scatters or changes direction without transforming into a different type of particle. A neutrino can bounce off an electron by exchanging a Z boson, and both the neutrino and the electron remain exactly what they were before the interaction. The Z boson transfers momentum and energy, but it does not rewrite identity. Only the W boson does that. Only the W boson can turn an up quark into a down quark, or a down quark into an up quark, or a charm quark into a strange quark, or any of the other allowed transitions between quark flavors. This distinction between the W and the Z is fundamental. The Z boson is neutral. It carries no electric charge. When it mediates an interaction, the particles on either side of the exchange retain their identity. The W boson is charged. When it mediates an interaction, the particles on either side must change to accommodate the charge that the W boson carries away or delivers. The charge forces the transformation. A down quark with charge -1/3 emits a W- with charge -1, and the quark must become something with charge +2/3 to keep the books balanced. That something is an up quark. The charge of the W boson is not incidental to its function. The charge is the mechanism by which it forces particles to change. This flavor-changing ability is not limited to the lightest quarks. The W boson can transform any quark into any other quark of a different type, as long as the quark changes between what physicists call the up-type family and the down-type family. The up-type quarks are the up quark, the charm quark, and the top quark. The down-type quarks are the down quark, the strange quark, and the bottom quark. A W boson can turn any up-type quark into any down-type quark, and vice versa. The transitions between different generations are suppressed, meaning they happen less often, but they are not forbidden. A charm quark can turn into a strange quark by emitting a W boson. A top quark can turn into a bottom quark. These heavier transitions are rarer because they involve larger mass differences, but the W boson makes all of them possible. The pattern of which transitions are more likely and which are less likely is described by a mathematical object called the quark mixing matrix, and measuring the precise values of that matrix has been one of the great experimental programs in particle physics over the past several decades. The W boson also acts on leptons, not just quarks. Leptons are the family of particles that includes the electron, the muon, the tau, and their associated neutrinos. When a W- boson decays, it can produce an electron and an electron antineutrino, or a muon and a muon antineutrino, or a tau and a tau antineutrino. Each of these outcomes happens with roughly equal probability because the W boson treats all three generations of leptons almost identically. The W boson is democratic in its destruction. It does not care which generation of particle it creates when it decays. It simply follows the rules of quantum mechanics, producing all allowed outcomes with probabilities determined by the masses and couplings involved. Now, let me tell you why all of this matters beyond the abstract realm of particle physics. The W boson is not just a curiosity of the subatomic world. It is one of the engines that powers the visible universe. Consider the Sun. The Sun generates energy by fusing hydrogen into helium in its core. The dominant process by which it does this is called the proton-proton chain. The very first step of that chain involves two protons colliding. For fusion to proceed, one of those protons must convert into a neutron. But a proton is made of two up quarks and one down quark, and a neutron is made of one up quark and two down quarks. To turn a proton into a neutron, one of its up quarks must become a down quark, and there is only one way that can happen. A W+ boson must be emitted. The up quark emits a W+ and becomes a down quark. The proton becomes a neutron. The W+ immediately decays into a positron and an electron neutrino. The positron quickly annihilates with a nearby electron, producing gamma rays that eventually work their way to the surface of the Sun as visible light. The neutrino flies straight out of the Sun at nearly the speed of light, passing through the entire star as if it were not there. This first step is also the slowest step. It is the bottleneck of the entire fusion chain, and it is the reason the Sun burns as steadily and as slowly as it does. The weak interaction is not efficient. The probability that two colliding protons will undergo this W boson-mediated conversion is fantastically small. On average, A given proton in the Sun's core will bounce off other protons for about 5 billion years before it finally undergoes this conversion. 5 billion years of failed collisions before one succeeds. That is how reluctant nature is to perform this transformation. And yet it happens constantly because there are so many protons in the Sun's core, roughly 10 to the power of 57 of them, colliding with each other at temperatures of about 15 million degrees. Even though any individual proton waits billions of years, the sheer number of protons means that the reaction happens roughly 10 to the power of 38 times every single second across the entire core. The Sun's steady glow, the fact that it does not explode like a bomb or fizzle out in a few years, is a direct consequence of how weak the weak interaction actually is. The W boson's massive weight suppresses the rate of this first step, throttling the fusion process into a slow, controlled burn that has lasted 4.5 billion years and will last roughly 5 billion more. Once that first step has occurred, once a proton has been converted into a neutron by the W boson, the rest of the chain follows relatively quickly. The newly formed neutron immediately binds with the remaining proton to form deuterium, a heavy isotope of hydrogen containing one proton and one neutron. This binding happens through the strong force and is nearly instantaneous compared to the weak interaction step that preceded it. The deuterium nucleus then collides with another proton, fusing to create helium-3, a light isotope of helium containing two protons and one neutron. A gamma ray is released in this step, carrying away energy. Finally, two helium-3 nuclei collide with each other and fuse to create one nucleus of helium-4, the ordinary helium you find in birthday balloons, containing two protons and two neutrons. Two leftover protons are released back into the plasma, free to begin the cycle again. The net result of the entire chain is that 4 protons have been converted into one helium-4 nucleus, 2 positrons, 2 neutrinos, and a collection of gamma rays. The helium-4 nucleus has slightly less mass than the 4 protons that went into making it. That missing mass has been converted into energy according to E equals mc squared. That energy is what powers the sun. That energy is what becomes the sunlight that warms your face. And the whole process, every single chain, begins with one W boson changing one quark inside one proton. Every second, the sun converts roughly 600 million tons of hydrogen into helium through this process. Every single one of those fusion reactions requires a W boson to mediate the conversion of a proton into a neutron. Without the W boson, that first step cannot happen. Without that first step, fusion in the sun does not proceed. Without fusion, the sun does not shine. Without the sun, the Earth is a frozen, lifeless rock in the darkness of space. The light warming your face on a summer afternoon exists because a W boson did its job inside the core of the sun. Every photon of sunlight you have ever seen began its journey because of a flavor-changing interaction mediated by a W boson deep inside a star. This is true not just for our sun, but for every hydrogen-burning star in the universe. The vast majority of stars you see in the night sky are main sequence stars fusing hydrogen into helium. Every one of them depends on the W boson to initiate that fusion. The W boson is one of the fundamental reasons the night sky is not completely dark. It is one of the reasons stars exist at all. The W boson's influence extends even further. The specific types of radioactive decay driven by the W boson determine which elements are stable and which are not. The entire structure of the periodic table, the pattern of stable and unstable isotopes, the specific forms of radioactive decay that certain atoms undergo, all of it is shaped by the W boson's properties. The rate at which a radioactive isotope decays depends on the strength of the weak interaction and the mass of the W boson. If the W boson were lighter, radioactive decays would happen faster, and the weak force would reach farther. If it were heavier, decays would be slower, and the force would be even more confined. The specific mass that the W boson actually has, 80.4 giga-electron volts, determines the precise balance of stability and instability across the entire periodic table. Change that mass even slightly, and the pattern of stable elements changes. Some currently stable atoms would become radioactive. Some currently radioactive atoms might become stable. The chemistry of the universe, and therefore the possibility of life, depends on the W boson having the mass it does. The W boson also played a critical role in the first minutes after the Big Bang. In those early moments, the universe was hot enough that W bosons were being produced freely, appearing and disappearing in enormous numbers. The interactions they mediated determined the ratio of protons to neutrons in the early universe. That ratio, which settled at roughly 7 protons for every neutron, determined how much helium was produced during Big Bang nucleosynthesis, the brief period about 3 minutes after the beginning, when the universe was cool enough for nuclei to form, but still hot enough for fusion to occur. The amount of primordial helium in the universe, about 25% by mass, is a direct consequence of weak interaction physics. Change the properties of the W boson, and you change that ratio. Change that ratio, and you change the chemical composition of the entire universe from its very beginning. There is also a deep and still not fully understood connection between the W boson and the dominance of matter over antimatter. The universe is made almost entirely of matter. For every billion or so particles in the early universe, there was roughly 1 extra particle of matter compared to antimatter. When matter and antimatter annihilated each other, that tiny surplus was all that remained. That surplus is everything you see. Every star, every planet, every atom in your body exists because of a slight asymmetry between matter and antimatter in the early universe. The weak interaction, mediated by the W boson, is one of the few places in physics where the symmetry between matter and antimatter is broken. Certain weak interaction processes involving the W boson proceed slightly differently for particles than for antiparticles. This violation of charge parity symmetry has been measured experimentally and is one of the necessary conditions for explaining why the universe contains matter rather than nothing. The W boson is implicated in one of the deepest unsolved mysteries in all of cosmology. Why does anything exist at all? So let us take stock of what the W boson does. It changes quark flavors, turning one type of quark into another. It connects neutrinos to the rest of the material world, acting as the chief bridge between those ghostly particles and ordinary matter. It drives beta decay, the process by which unstable atomic nuclei shed excess energy by converting neutrons to protons or protons to neutrons. It powers the first step of nuclear fusion in stars, making sunlight and starlight possible. And the slowness of that step is the reason stars burn steadily for billions of years, rather than detonating in an instant. It determined the balance of protons and neutrons in the early universe, setting the primordial chemical composition. It participates in the violation of matter-antimatter symmetry that may explain why the universe is not empty. And it interacts only with left-handed particles, breaking the mirror symmetry of nature in a way that no other force does. All of this is done by a particle that cannot survive long enough for light to cross a proton. All of this is done in a space smaller than the smallest atomic nucleus. The W boson is confined to an almost inconceivably tiny stage. But on that stage, it performs the most consequential act in all of particle physics. It changes what things are. It rewrites the identity of matter. And through that single ability, it shapes the structure and composition of the entire visible universe. The question that should be burning in your mind right now is why? Why is the W boson so heavy? What gives it that enormous mass that confines it to such a tiny range and destroys it so quickly? The answer involves a field that fills all of space. A field that interacts with the W boson in a way that slows it down, weighs it down, and seals its fate. That field and that mechanism are what we turn to next. There is a question hiding at the center of everything we have discussed so far. We know the W boson is massive. We know that mass confines it to a range smaller than a proton and kills it in a time shorter than light could cross that range. We know that mass is the reason the weak force is weak, the reason it cannot reach across space the way electromagnetism does. But we have not yet asked the most important question. Where does that mass come from? Why is the W boson heavy at all? This is not a trivial question. In fact, for decades, it was one of the deepest puzzles in all of particle physics. The equations governing the weak interaction, when written in their most natural form, do not allow the W boson to have mass. The symmetry of the theory forbids it. If you simply insert a mass term for the W boson by hand, the mathematics breaks. The theory becomes inconsistent. It produces infinite answers for quantities that should be finite. It stops making sense. And yet the W boson clearly has mass. Experiments confirm it. The weak force clearly has a short range. Reality insists on it. So something must be generating that mass. Something that gives the W boson its enormous weight without destroying the mathematical consistency of the theory. That something is the Higgs field. To understand why the W boson's mass was such a problem, you need to appreciate something about the role of symmetry in physics. Symmetry is not just an aesthetic quality, it is a structural principle. The fundamental forces of nature are described by mathematical objects called gauge symmetries, and these symmetries dictate what particles exist, how they interact, and what properties they can have. Electromagnetism, for example, is governed by a symmetry that physicists label U1. This symmetry requires that the photon be massless. If you tried to give the photon a mass, you would break the U1 gauge symmetry, and the theory of electromagnetism would become mathematically inconsistent. Fortunately, the photon is massless, so no problem arises. The weak interaction, together with electromagnetism, is described by a larger symmetry group called SU2 cross U1. This is the electroweak symmetry. It unifies the weak force and the electromagnetic force into a single mathematical framework. And just like the simpler electromagnetic symmetry requires the photon to be massless, the electroweak symmetry requires all four of its force carriers to be massless. All four: the photon, the W+, the W-, and the Z boson. According to the raw symmetry of the theory, none of them should have mass, but three of them do. The W+, the W-, and the Z boson are among the heaviest elementary particles known. Something has broken the electroweak symmetry, not destroyed it, but hidden it, disguised it so that at the low energies we experience in daily life, the symmetry appears to be absent, even though it still governs the underlying equations. The mechanism that does this is called spontaneous symmetry breaking, and the agent of that breaking is the Higgs field. The Higgs field is not a particle. It is a field that fills all of space, everywhere, at all times. It has no gaps, it has no edges. Every point in the universe, from the center of a star to the emptiest void between galaxies, is permeated by the Higgs field. You are moving through it right now. Every atom in your body is immersed in it. It is as omnipresent as space itself. But unlike most quantum fields, which have a value of 0 in their lowest energy state, the Higgs field has a non-zero value everywhere. Its lowest energy state, its ground state, is not empty. It is full. The field is always on, always present, always filling space with a constant background value. This non-zero background value is what breaks the electroweak symmetry. The underlying equations still have the full SU2 cross U1 symmetry. Nothing about the fundamental laws has changed. But the state of the universe, the actual physical configuration of the Higgs field, does not respect that symmetry. The field has chosen a particular direction in an abstract internal space, and that choice breaks the symmetry spontaneously. It is like a ball sitting at the top of a perfectly symmetric hill. The hill is symmetric. Every direction downward is equivalent. But the ball must roll somewhere, and when it does, it picks a direction. The symmetry is broken not by the laws governing the ball, but by the ball's actual position. Let me give you a more physical analogy. Imagine a perfectly flat, frozen lake. The ice is smooth in every direction. If you were standing on it, no direction would be special. North, south, east, west, the ice looks the same everywhere. This is like the unbroken electroweak symmetry. Every direction is equivalent. Now imagine that the temperature drops further and the ice develops a crystalline structure. Suddenly, the ice has grain lines running in specific directions. The underlying physics, the laws governing water molecules, do not prefer any direction. But the actual crystal that formed has picked one. The symmetry is broken by the state of the material, not by the laws governing it. The Higgs field does something analogous to the vacuum of space. It fills the vacuum with a preferred configuration that breaks the electroweak symmetry, even though the fundamental equations remain symmetric. This is not just an abstract mathematical statement. It describes something that actually happened. There was an era in the history of the universe when the electroweak symmetry was unbroken, when the Higgs field had not yet settled into its current non-zero value, when the W boson was massless. That era was extraordinarily brief and extraordinarily violent, and it ended roughly 10 to the power of -12 seconds after the Big Bang, 1/trillionth of a second. Before that moment, the universe was so fantastically hot, with temperatures exceeding 10 to the power of 15 degrees, that the thermal energy filling space was more than enough to overpower the Higgs field. The field was there, but the energy of the environment kept it from settling into its preferred non-zero state. It was like trying to freeze water in the heart of a furnace. The conditions would not allow it. In that blistering era, the electroweak symmetry was intact. There was no distinction between the electromagnetic force and the weak force. They were one force, carried by 4 massless particles that behaved identically in almost every way. The W boson, if you could even call it that, was as light as the photon. It travelled at the speed of light. It could reach across any distance. The weak interaction was not weak at all. It was just as strong and just as far-reaching as electromagnetism, because its carriers had no mass to hold them back. The universe at this stage was a dense, ferocious plasma of quarks, gluons, leptons, and gauge bosons, all interacting with each other at energies that would make the most powerful particle accelerator on Earth look like a toy. Particles were being created and annihilated constantly. The W boson was everywhere, mediating interactions as freely as the photon. Neutrinos were in constant contact with the rest of matter, scattering and interacting as readily as electrons. Nothing was stable. Nothing was permanent. Everything was energy and transformation, a churning sea of particles being born and destroyed trillions of times per second. Then the universe cooled. As space expanded, the temperature dropped, and at some point, roughly 1/1,000,000,000 of a second after the beginning, the temperature fell below the critical threshold. The Higgs field, no longer overwhelmed by thermal energy, settled into its non-zero ground state. It was like a phase transition, like water crystallizing into ice. The vacuum of space changed its character. The Higgs field pervaded all of space with its constant background value, and in that instant, the electroweak symmetry broke. 3 of the 4 electroweak force carriers suddenly acquired enormous mass. The W+, the W-, and the Z boson went from being massless particles traveling at the speed of light to being among the heaviest particles in existence. The 4th carrier, the photon, remained massless. Electromagnetism and the weak force, which had been one force for the first trillionth of a second, separated into 2 forces with radically different properties. The weak force, now carried by massive bosons, shrank to a range smaller than a proton. Electromagnetism, still carried by the massless photon, kept its infinite reach. The universe you live in, the one with stable atoms and chemistry and starlight and life, began to take shape in that moment. The Higgs field is entirely responsible for this split, but knowing that the symmetry broke is not the same as knowing how the Higgs field actually gives the W boson its mass. The mechanism is specific, physical, and worth understanding in detail. The answer comes down to interaction. The W boson interacts with the Higgs field. It couples to it strongly. As a W boson moves through space, it is constantly interacting with the ever-present Higgs field, and that interaction behaves in a way that is mathematically identical to the W boson having mass. Think of it this way. Imagine a person trying to walk through an empty room. They move freely. There is nothing to slow them down. They cross the room at whatever speed they choose. Now imagine the room is filled with a thick, invisible substance, something like a dense syrup that permeates every corner. As the person tries to walk, the syrup resists their motion. It takes more effort to accelerate. It takes more effort to change direction. The person behaves as though they are heavier, as though they have more inertia, even though nothing has been added to their body. The syrup has given them effective mass by resisting their motion. The Higgs field does something similar to the W boson. The W boson couples strongly to the Higgs field, and that coupling gives it inertia. It behaves as a massive particle because the Higgs field resists changes in its state of motion. The stronger a particle couples to the Higgs field, the more mass it acquires. The W boson couples strongly, so it acquires a large mass. The Z boson also couples strongly, acquiring an even larger mass of about 91.2 giga-electron volts. The photon does not couple to the Higgs field at all in the way that generates mass, so it remains massless. This is not an accident. It is a precise consequence of how the symmetry breaking works. The photon corresponds to a particular combination of the original electroweak fields that happens to be aligned with the direction the Higgs field chose when it broke the symmetry. Because it is aligned, it does not interact with the Higgs background in a way that generates mass. The W and Z bosons correspond to combinations that are not aligned with the Higgs field's chosen direction, so they interact with it and acquire mass. The entire pattern of masses, which particles are heavy, which are light, and which are massless, emerges from the geometry of symmetry breaking. This mechanism was proposed in 1964, independently and nearly simultaneously by 3 groups of physicists. Peter Higgs in Edinburgh wrote a paper describing how a scalar field could break gauge symmetry and give mass to force carriers. François Englert and Robert Brew in Brussels published a closely related paper with the same essential idea. And Gerald Alnick, Carl Hagen, and Tom Kibble in London developed the mechanism in yet another independent paper. All three groups recognize the same fundamental point. A quantum field with a non-zero vacuum value could break a gauge symmetry spontaneously, and in the process, some of the originally massless gauge bosons would acquire mass. The particle associated with this field, the quantum excitation of the Higgs field itself, is what we now call the Higgs boson. It was predicted to exist as a detectable particle, a ripple in the Higgs field, and in 2012, nearly half a century after its prediction, it was discovered at the Large Hadron Collider at CERN. The ATLAS and CMS experiments independently observed a new particle with a mass of about 125 giga-electron-volts, and its properties matched the predictions for the Higgs boson with remarkable precision. That discovery confirmed that the Higgs field is real, that it fills all of space, and that it is responsible for the masses of the W and Z bosons. Now we come to the heart of the matter. Why does the W boson's mass make it die so fast? The answer lies in one of the most fundamental principles of quantum mechanics, the energy-time uncertainty relation. This is a close relative of the more famous position-momentum uncertainty principle formulated by Werner Heisenberg in 1927. The energy-time version says that the uncertainty in a particle's energy, multiplied by the uncertainty in the time interval during which that energy is defined, must be at least as large as a specific tiny constant, h bar divided by 2. H bar is the reduced Planck constant, one of the fundamental numbers of quantum mechanics. What this means in practical terms is that nature allows temporary violations of energy conservation, but only for very short times. The larger the energy fluctuation, the shorter the time it can last. The smaller the fluctuation, the longer it can persist. Energy and time are linked by a fundamental trade-off. You can borrow a lot of energy, but you must pay it back quickly. You can borrow a little energy and take your time returning it. This principle governs the existence of every unstable particle. When a W boson is created as a real particle, for example in a high-energy collision at the Large Hadron Collider, it carries an enormous amount of energy locked up in its mass, 80.4 giga-electron-volts worth. That energy is available to be redistributed. The W boson can decay into lighter particles, converting its mass energy into the kinetic energy and rest masses of its decay products. And because there are many lighter particles it can decay into, and because the coupling strengths involved are not small, the decay happens extraordinarily quickly. The rate at which a particle decays is determined by two things. First, how many different ways it can decay. Each possible set of decay products is called a decay channel. The W- boson can decay into an electron and an electron antineutrino. It can decay into a muon and a muon antineutrino. It can decay into a tau and a tau antineutrino. It can also decay into quark-antiquark pairs, such as an up quark and a down antiquark, or a charm quark and a strange antiquark. Each of these channels contributes to the total decay rate. The more channels available, the faster the particle decays, because there are more ways for nature to spend the energy. Second, the decay rate depends on the coupling strength. How strongly the W boson interacts with the particles it decays into. The weak interaction coupling constant is not actually that small. The word weak is misleading. The intrinsic strength of the weak coupling is comparable to that of the electromagnetic coupling. The weak force appears weak only because the W boson's mass suppresses its effects at low energies. At energies comparable to the W boson's mass, the weak interaction is not weak at all. It is roughly the same strength as electromagnetism. This means the W boson decays readily into its allowed products. The coupling is strong enough, and the number of available channels is large enough that the total lifetime is incredibly short. Let me walk you through the actual accounting so you can see exactly why the W boson has so many exit doors. Start with the leptonic channels. The W- can decay into an electron and an electron antineutrino. That is one channel. It can decay into a muon and a muon antineutrino. That is a second channel. It can decay into a tau and a tau antineutrino. That is a third channel. 3 leptonic channels in total. Each one contributes roughly equally to the total decay rate because the W boson couples to all 3 generations of leptons with essentially the same strength, and the lepton masses are small enough compared to the W boson's mass that they barely affect the calculation. Now consider the quark channels. The W- can decay into an up antiquark and a down quark. It can also decay into a charm antiquark and a strange quark. It could, in principle, decay into a top antiquark and a bottom quark, but the top quark is too heavy. Its mass is about 173 giga-electron volts, which is more than twice the W boson's mass of 80.4 giga-electron volts. There is simply not enough energy available, so this channel is closed. That leaves 2 open quark channels, an up antiquark with a down quark and a charm antiquark with a strange quark. But here is the crucial detail. Quarks come in 3 varieties of color charge. Color charge is the property that the strong force acts upon, analogous to electric charge for electromagnetism. Every quark can be red, green, or blue. These are not literal colors, just labels for 3 distinct quantum states. When the W boson decays into a quark-antiquark pair, the pair can be produced in any of 3 color combinations. This means each quark decay channel actually counts as 3 channels, 1 for each color. 2 quark channels times 3 colors gives 6 effective quark channels. Add it all up. 3 leptonic channels plus 6 quark channels gives 9 total channels. Each channel acts like a separate exit door through which the W boson's energy can escape. The more doors, the faster the room empties. If the W boson had only 1 decay channel, it would live longer. If it had 30, it would die even faster. 9 channels, combined with a coupling strength that is comparable to electromagnetism, produces the extraordinarily short lifetime we observe. The branching ratios, the fractions of W boson decays that go into each channel, reflect this counting directly. About 1/9 go into electrons and electron antineutrinos. About 1/9 go into muons and muon antineutrinos. About 1/9 go into taus and tau antineutrinos. That means about 1/3 of all W boson decays produce leptons. The remaining 2/3 produce quarks. This prediction of the Standard Model has been tested extensively at particle colliders, and the measured branching ratios match the theoretical predictions with impressive precision. The accounting works. Nature counts exit doors exactly the way the theory says it should. Let me walk you through the numbers so you can feel how mass and lifetime are connected. The W boson has a measured decay width of about 2.08 giga-electron volts. In particle physics, the decay width is inversely related to the lifetime. A larger width means a shorter life. You can convert the width directly into a lifetime using the energy-time uncertainty relation. When you do the conversion, you get a lifetime of approximately 3.2 times 10 to the power of -25 seconds. That number deserves some context. The shortest time interval you could consciously perceive is perhaps a few tens of milliseconds. A millisecond is 10 to the -3 seconds. The W boson's lifetime is 10 to the -25 seconds. That is 22 orders of magnitude shorter than a millisecond. If you started counting from 1 millisecond and divided it by 10, over and over, 22 times, you would arrive at the W boson's lifetime. Each division makes the interval 10 times shorter. 22 such divisions is a reduction by a factor of 10,000 billion billion. That is how brief the W boson's existence is. During that time, how far can the W boson travel? Even moving at the speed of light, which is the absolute maximum speed anything can attain, a particle travelling for 3.2 times 10 to the negative 25 seconds covers a distance of about 10 to the negative 16 meters. That is 1/10 of a femtometer. A proton has a diameter of roughly 1.7 femtometers. So the W boson, even at the speed of light, could not cross the width of a single proton before it decays. In practice, W bosons produced in particle colliders do not travel at the speed of light because they have mass. They move slower. So the actual distance they cover before decaying is even shorter. They are born and they die within a volume smaller than a single proton. No detector can see them directly. We only see what they leave behind. Now contrast this with the photon. The photon has 0 mass and 0 decay width. It does not decay. It cannot decay into lighter particles because there are no lighter particles for it to decay into while conserving energy, momentum, and all the relevant quantum numbers. A photon, once created, will travel forever unless something absorbs it. There is no internal clock ticking down to its destruction. There is no energy debt to repay. It exists indefinitely at 0 cost, because it carries 0 mass energy beyond its kinetic energy, and that kinetic energy is perfectly stable. The difference between the photon and the W boson is entirely explained by mass. The photon has no mass and lives forever. The W boson has enormous mass and lives for almost no time at all. Mass is not just a number on a datasheet. Mass is a death sentence. The heavier a particle is, the more energy it carries locked inside it, the more ways that energy can be redistributed into lighter particles, and the faster the decay occurs. This is a general principle that applies across the entire Standard Model. The top quark, the heaviest known fundamental particle, at about 173 giga-electron volts, decays in roughly 5 times 10 to the power of negative 25 seconds, slightly longer than the W boson despite being heavier, because it has fewer available decay channels. The Z boson, slightly heavier than the W, at about 91.2 giga-electron volts, has a lifetime of roughly 3 times 10 to the power of negative 25 seconds, comparable to the W bosons. The pattern is consistent. Heavy particles die fast. The connection between mass, lifetime, and range is what shapes the entire character of the weak force. Because the W boson is heavy, it cannot exist for long. Because it cannot exist for long, it cannot travel far. Because it cannot travel far, the force it carries has a tiny range. If the W boson were massless, the weak force would be a long-range force, reaching across infinite distances, just like electromagnetism. The universe would be completely different. Radioactive decay would work differently. Stellar fusion would proceed at a different rate. The balance between protons and neutrons in the early universe would have been different. The very elements that make up your body might not exist. The mass of the W boson is not some incidental detail of particle physics. It is one of the architectural decisions that determines the structure of reality. And this mass comes entirely from the Higgs field. Without the Higgs field, the electroweak symmetry would be unbroken. The W boson would be massless. It would travel at the speed of light and live forever. The weak force would have the same infinite range as electromagnetism. In fact, the two forces would be indistinguishable. There would be no separate weak force and electromagnetic force. There would be one electroweak force with 4 massless carriers, and the universe would look nothing like the one you live in. The Higgs field changed everything. By acquiring a non-zero value throughout all of space, it broke the electroweak symmetry, gave the W and Z bosons their enormous masses, and confined the weak interaction to subatomic distances. It separated electromagnetism from the weak force. It created the distinction between a force that reaches across the cosmos and a force that barely reaches across a proton. And in doing so, it determined the rates of radioactive decay, the pace of stellar fusion, the chemical composition of the universe, and the stability of the matter in your body. All because of a field that quietly fills every point in space with a constant non-zero value. There is something philosophically striking about this picture. The W boson is not held back by some external barrier. There is no wall keeping it from traveling farther. There is no cage confining it to the inside of a proton. The W boson is held back by space itself, or rather, by what fills space. The Higgs field is everywhere. The W boson interacts with it everywhere, and that interaction gives the W boson a mass so large that it cannot survive long enough to travel any meaningful distance. The prison is built into the fabric of the vacuum. The W boson lives in a universe where the very emptiness of space conspires to make it heavy and to make it short-lived. If you could somehow switch off the Higgs field, if you could restore the electroweak symmetry, the W boson would be freed. It would lose its mass, gain infinite range, and live forever. But you cannot switch off the Higgs field. It is as fundamental a feature of our universe as space and time themselves. The W boson is born heavy and it dies fast, because the universe it was born into is one where the Higgs field has already made its choice. This also means that the W boson's death is not a flaw. It is not a deficiency. It is the price of living in a universe with broken electroweak symmetry. A universe where matter has the structure it does, where chemistry works the way it does, where stars burn and atoms are stable and life is possible. The same mechanism that kills the W boson so quickly is the mechanism that makes the physical world recognizable. Without the Higgs field, the W boson would be immortal, but nothing else about the universe would be familiar. No stable atoms, no chemistry, no complexity, no life. The W boson's rapid death is, in a deep sense, the cost of a universe where anything interesting can happen. You now understand where the W boson's mass comes from. It comes from the Higgs field, a quantum field with a non-zero value filling all of space, which breaks the electroweak symmetry and gives the W and Z bosons their enormous masses while leaving the photon massless. You understand why that mass makes the W boson die so fast. The energy-time uncertainty relation links mass to instability. A heavy particle carries enormous energy that can be redistributed into lighter particles, and the more ways that redistribution can happen, the faster it occurs. The W boson has 9 effective decay channels and a coupling strength comparable to electromagnetism, so it decays in roughly 3 × 10⁻⁻25 seconds. You understand why that short lifetime confines the weak force to subatomic distances. The W boson cannot travel farther than about 10⁻⁻16 meters before it decays, and this sets the range of the force it carries. And you understand that all of this, the mass, the lifetime, the range, the very distinction between the weak force and electromagnetism, originates in the Higgs field's decision to fill empty space with a non-zero value. A decision that was made 1/1,000,000,000 of a second after the birth of the universe, and that has shaped every moment of physical reality since. But one question remains, the biggest question of all, the one in the title. If the W boson is so massive, if it has so much energy packed into it, if it can decay into quarks and leptons, then what is it made of? Is it built from smaller pieces? Does it contain quarks or some other substructure? Or is it something else entirely? Something that challenges our intuition about what a fundamental object can be? That question is where we go next. We have arrived at the question that has been quietly waiting behind everything else. The question in the title. What is the W boson made of? You might expect a complicated answer. You might expect that a particle so massive, so consequential, so central to the architecture of the universe must be built from something. After all, that has been the pattern throughout the history of science. Every time physicists found something they thought was fundamental, they eventually discovered it was made of smaller pieces. Molecules are made of atoms. Atoms are made of electrons, protons, and neutrons. Protons and neutrons are made of quarks and gluons. Each layer peeled back to reveal a deeper layer underneath. Surely the W boson, weighing as much as an atom of strontium, must contain something inside it. Surely a particle that heavy cannot be truly elementary. But as far as every experiment ever performed and every theoretical framework we currently possess can tell us, the W boson is not made of anything. It has no internal parts. It has no substructure. It is not built from quarks. It is not assembled from smaller bosons. It is not a bound state of more fundamental particles. The W boson, despite its enormous mass, is elementary. It is fundamental. It is one of the irreducible building blocks of reality, as described by the standard model of particle physics. To understand what this means, you need to understand what modern physics means by the word fundamental. It does not mean what the ancient Greek philosopher Democritus meant when he proposed that matter was made of indivisible atoms. Democritus imagined tiny, hard, impenetrable balls that could not be cut in half. His atoms were little objects, miniature versions of the solid things we see in everyday life, just too small to break apart. Modern physics has a very different concept. In modern physics, a fundamental particle is not a tiny ball. It is not a solid object at any scale. A fundamental particle is the simplest possible excitation of a quantum field. It is the smallest possible disturbance, the most basic ripple, the lowest unit of activity that a particular field can produce. The W boson is a fundamental excitation of the weak force quantum field. Just as a photon is the most basic ripple in the electromagnetic field, the W boson is the most basic ripple in the field associated with the charged component of the weak interaction. There is nothing simpler that this field can do. There is no half ripple, no partial W boson, no subcomponent vibrating inside it. The field either produces a W boson or it does not. The W boson is the minimum unit of what that field can create. This is a profoundly different way of thinking about what things are made of. In everyday life, when you ask what something is made of, you are asking about its internal composition. A table is made of wood. Wood is made of cellulose fibers. Cellulose is made of glucose molecules. You are looking for smaller pieces inside the larger thing. But at the most fundamental level of physics, this chain of made of simply ends. The W boson is not made of smaller things in the way a proton is made of quarks. A proton has internal structure. You can scatter electrons off a proton and see that the electrons bounce off at specific angles, revealing the presence of point-like objects inside. This is exactly what the deep inelastic scattering experiments of the late 1960s and early 1970s showed. They revealed quarks inside protons and neutrons. The scattering patterns were unmistakable. the proton has parts. The W boson does not show this behavior. When physicists probe the W boson at the highest energies available, when they study how it is produced and how it decays, when they measure its properties with extraordinary precision, they find no evidence of internal structure, no scattering pattern suggestive of subcomponents, no anomalous behavior that would hint at a deeper layer. The W boson, to the limits of our current experimental capability, behaves exactly as a point-like fundamental particle should. The experimental evidence for this comes from decades of precision measurements at particle colliders around the world. The LEP collider at CERN, which operated from 1989 to 2000, produced millions of W boson pairs and measured their properties with exquisite accuracy. The mass, the decay width, the branching ratios into different decay channels, the angular distributions of the decay products, all of these were measured and compared with the predictions of the standard model. The agreement was outstanding. If the W boson had internal structure, that structure would modify its behavior in ways that would show up as deviations from standard model predictions. The decay rates would be slightly different. The angular distributions would have subtle anomalies. The cross-sections for producing W bosons would depart from calculated values at high energies. None of these deviations have been observed. The LEP experiments, including Aleph, Delphi, L3 and Opal, all confirmed that the W boson behaves as a fundamental particle to the precision they could achieve. The Large Hadron Collider has pushed these tests further. The LHC produces W bosons in enormous numbers, millions upon millions of them, allowing measurements of unprecedented statistical precision. The ATLAS and CMS experiments have measured the W boson's mass to better than 15 mega-electron-volts of precision. They have studied its production in association with jets of quarks and gluons, looking for subtle signs of new physics or substructure. They have examined the highest energy collisions available, where the effects of any internal structure would be most visible. And every result is consistent with the W boson being a point-like fundamental particle with no internal parts. This does not prove the W boson has no substructure. It is impossible to prove a universal negative with finite experiments. But it means that if the W boson does have internal structure, that structure must be hidden at energy scales far beyond what our current accelerators can probe. The W boson looks fundamental down to distances of at least 10 to the power of -19 meters. That is about 1/10,000th the diameter of a proton. At every scale we can currently resolve, the W boson has no inside. Now, let me address the intuition that rebels against this conclusion. It feels wrong that something so heavy should be elementary. We are accustomed to the idea that mass comes from structure. A proton is heavy because it contains quarks and gluons bound together by the strong force, and most of the proton's mass actually comes from the energy of those gluons and the kinetic energy of the quarks, not from the quark's own tiny masses. The proton's mass is a consequence of its complexity. It has parts, and those parts interact in energetic ways, and that interaction energy contributes to the mass through E equals mc². So when you encounter a particle even heavier than a proton, your instinct says it should be even more complex, with even more parts interacting even more energetically. But the W boson breaks this pattern. Its mass does not come from internal complexity. Its mass comes from its interaction with the Higgs field. As we explored earlier, the Higgs field fills all of space with a non-zero value, and the W boson couples to this field strongly. That coupling gives the W boson its mass directly, without requiring any internal substructure at all. The mass is not generated by parts bouncing around inside the W boson. It is generated by the W boson's relationship with the vacuum itself, with the Higgs field that permeates every point in space. This is a fundamentally different mechanism of mass generation than the one operating inside a proton, and it does not require the W boson to have internal complexity. This is worth sitting with for a moment, because it reveals something deep about the nature of mass. Not all mass works the same way. The mass of a proton comes mostly from the strong force energy binding its quarks and gluons together. The mass of a W boson comes from its coupling to the Higgs field. The mass of a composite object like a rock comes from the masses of its atoms, which come from the masses of their nuclei, which come from both the quark masses given by the Higgs field and the binding energy of the strong force. Mass has multiple origins, and the type of mass the W boson possesses, Higgs-generated mass, does not require any internal structure whatsoever. A truly point-like, structureless particle can be extremely heavy if it couples strongly enough to the Higgs field. This is one of the great insights of the Standard Model. There is another way to understand why the W boson can be both heavy and fundamental. Think about what a quantum field is. The electromagnetic field exists everywhere in space. When that field is in its ground state, its lowest energy state, we say the field is in its vacuum state. There are no photons present, but the field is still there, ready to be excited. When something disturbs it, when a charged particle accelerates, for example, the field produces a photon. That photon is a quantum of the electromagnetic field. It is not made of anything smaller. It is simply what happens when the electromagnetic field is excited by the minimum possible amount. The photon can carry different amounts of energy depending on its frequency, but the photon itself is the irreducible minimum disturbance of that field. The weak force field works the same way. It exists everywhere in space. When conditions are right, when enough energy is concentrated in a small enough volume, the field produces a W boson. That W boson is a quantum of the weak force field, the minimum disturbance that field can produce. It happens to be a very energetic minimum disturbance because the Higgs field has given the weak force field a particular property, a mass gap. The field cannot be excited by anything less than 80.4 giga-electron-volts of energy. Below that threshold, no W boson is produced. The field remains in its ground state. Above that threshold, the minimum excitation, the single W boson, springs into existence. Its enormous mass is a property of the field itself, shaped by the field's interaction with the Higgs field. It is not a property of internal components because there are no internal components. Let me say this as plainly as I can. When you ask what the W boson is made of, the most honest answer modern physics can give is this. The W boson is made of field. It is a localized excitation of a quantum field that permeates all of space. It is a ripple, a disturbance, a vibration. It is the weak force field doing the simplest thing it can do. And the reason that simplest thing is so heavy is that the Higgs field has shaped the properties of the weak force field in a way that requires a massive minimum energy to create even one ripple. The W boson is not made of quarks, not made of preons, not made of strings, not made of anything you can decompose. It is a single, indivisible quantum event in a field that fills the universe. That said, I should be honest about the limits of our knowledge. The Standard Model is not necessarily the final word. It describes the W boson as a fundamental particle with no internal structure, and every experiment conducted to date agrees with that description. But the Standard Model is almost certainly not a complete theory of nature. It does not include gravity in a quantum mechanical way. It does not explain dark matter or dark energy. It has features that seem arbitrary, like the specific values of the particle masses and coupling constants, which the Standard Model takes as inputs rather than deriving from first principles. There are many unanswered questions in particle physics, and some of those unanswered questions could eventually reveal that the W boson has structure at scales we cannot yet probe. Speculative theories do exist that propose deeper layers of reality beneath the Standard Model. One class of theories involves hypothetical particles called preons. The idea of preons dates back to the late 1970s. Physicists like Yogesh Tati and Abdus Sulam, and independently Chaim Harari and Michael Shoup, proposed that quarks and leptons might themselves be made of even more fundamental objects. In some of these models, the W boson would also be composite, a bound state of preons held together by a new force that operates at extremely high energies. If preons exist, they would represent a new layer of reality beneath the Standard Model, and particles we currently regard as fundamental, including the W boson, would turn out to be composite after all. But there is no experimental evidence for preons. No experiment has found any hint of quark or lepton substructure. No deviations from Standard Model predictions have been observed that would point toward compositeness. The energy scales at which preon structure would become visible are far beyond the reach of any existing or planned accelerator. Preon models are not ruled out, but they are not supported by data either. They remain a theoretical possibility, not an established fact. Other speculative frameworks like string theory propose that all particles, including the W boson, are ultimately different vibrational modes of tiny one-dimensional objects called strings. In string theory, the W boson would not be a point particle. It would be a string vibrating in a specific pattern, with the pattern determining its mass, charge, and other properties. But string theory operates at the Planck scale, roughly 10 to the power of negative 35 meters, which is about 16 orders of magnitude smaller than the distances probed by the Large Hadron Collider. There is currently no way to test whether the W boson is a vibrating string. String theory is a mathematically rich and theoretically motivated framework, but it has not yet produced a testable prediction that distinguishes it from the Standard Model at accessible energies. So where does this leave us? The honest answer is that the W boson is fundamental as far as we can currently tell. The Standard Model describes it as a point-like elementary particle with no internal structure, and every experiment agrees. Speculative theories propose deeper layers of reality where the W boson might turn out to be composite or to have structure at extraordinarily small scales, but these proposals remain unconfirmed. The W boson sits at the current bottom of the ladder of structure. It is one of the particles at which the chain of "what is it made of" simply stops. It is made of field. It is a quantum of the weak interaction. And until new experiments or new theories give us reason to think otherwise, that is the best and most accurate answer physics can offer. Let me close by reflecting on what the W boson reveals about the universe you live in. Here is a particle that is one of the heaviest elementary objects ever directly observed. It is so massive that creating one requires the energy of roughly 86 protons. And yet it is not built from parts. It is not assembled from pieces. It is a fundamental ripple in a quantum field, given its enormous mass by the Higgs field that fills all of space. That mass seals its fate. The W boson cannot exist for more than roughly 3 times 10 to the power of negative 25 seconds. It cannot travel farther than a fraction of a proton's width. It is born, it acts, and it vanishes in a time so short that the word instant is too generous. And yet, in that immeasurably brief moment, it does something no other particle in nature can do. It changes the identity of matter. It turns one type of quark into another. It converts neutrons into protons and protons into neutrons. It bridges the gap between neutrinos and everything else. It rewrites the fundamental character of the particles it touches. That transformation powers the stars. Every hydrogen-fusing star in the universe, every point of light in the night sky that shines by nuclear fusion, depends on the W boson to mediate the first and most difficult step of the fusion chain. Without the W boson, no proton could become a neutron inside the Sun's core. Without that conversion, fusion would not proceed. Without fusion, no starlight. Without starlight, no warmth, no energy, no photosynthesis, no complex chemistry, no life. The light that sustains you began its journey because a W boson appeared for a trillionth of a second deep inside a star. That transformation also shaped the elements. Every radioactive decay driven by the weak interaction, every beta decay that shifts an atom from one element to another, is the W boson at work. The pattern of stable and unstable isotopes across the entire periodic table is determined by the W boson's properties, by its mass, its coupling strength, and the specific rules governing which transitions it allows. Change the mass of the W boson by even a small fraction, and the periodic table changes. Elements that are stable become unstable. Elements that are radioactive become stable. The chemistry of the universe reshuffles, and the particular combination of elements necessary for life may no longer exist. That transformation also determined the composition of the universe itself. In the first minutes after the Big Bang, when the cosmos was a dense sea of particles and radiation, the W boson mediated the reactions that set the ratio of protons to neutrons. That ratio determined how much primordial helium was produced. It determined the starting conditions for the chemical evolution of the entire universe. Every heavy element forged later in the cores of massive stars and in the violence of supernovae was built upon a foundation of hydrogen and helium whose relative abundances were fixed by the W boson in the earliest moments of cosmic history. And that transformation may hold the key to the deepest mystery of all. Why does anything exist? The universe is made of matter, not antimatter. For every billion particle-antiparticle pairs that annihilated in the early universe, roughly one extra particle of matter survived. That tiny asymmetry is everything. Every galaxy, every star, every planet, every atom in your body exists because of it. The weak interaction, mediated by the W boson, is one of the few places in physics where the symmetry between matter and antimatter is violated. The W boson participates in processes that treat matter and antimatter slightly differently. This asymmetry is measured, confirmed, and built into the structure of the Standard Model. Whether it is sufficient on its own to explain the full matter-antimatter imbalance in the universe remains an open question. But the W boson is implicated. It is part of the mechanism that made a universe of something rather than a universe of nothing. All of this from a particle with no parts. All of this from a ripple in a quantum field that lasts for less time than light needs to cross a fraction of a proton. The W boson is a study in contrasts. It is massive but fundamental. It is powerful but short-lived. It is essential to the structure of the universe but invisible to any direct observation. It cannot be seen, only inferred. It cannot survive, only act. It changes matter, and then it is gone, leaving behind only the transformed particles and the energy of its decay. If you zoom in far enough on any physical process in the universe that involves a change of particle identity, somewhere at the heart of it you will find a W boson. Every time a neutron decays inside a radioactive atom, a W boson was there. Every time a proton converts to a neutron inside a star, a W boson was there. Every time a neutrino interacts with anything at all, a W or Z boson was there. The W boson is the hidden mechanism behind some of the most important processes in nature, and it performs its work in a space smaller and a time shorter than almost anything else in physics. So what is the W boson made of? It is made of the same thing all fundamental particles are made of: field, quantum field, the weak force field that fills all of space, shaped by the Higgs field into a form that demands enormous energy for the simplest excitation, producing a particle that is heavy, charged, unstable, and transformative. The W boson is not a container holding smaller things, it is an event. A quantum event in a field that exists everywhere. And that event, brief and violent and impossibly small, is one of the foundations on which the visible universe is built. You are made of atoms. Those atoms were forged in stars. Those stars were powered by fusion reactions that could not begin without the W boson. The carbon in your cells, the oxygen in your lungs, the iron in your blood. All of it traces a chain of nuclear processes that ultimately depends on a particle that lives for 3 × 10⁻⁻25 seconds and has no known internal structure. You are here because a quantum field ripples in a certain way, because the Higgs field gave that ripple an enormous mass, because that mass forced the ripple to be brief, and because in that briefness the ripple still had time to change one quark into another inside the core of a star billions of years ago. The W boson is one of the most important particles you have never seen and will never see. And now you know what it is, why it dies so fast, and why the answer to what it is made of is both the simplest and the strangest answer physics can give. Nothing. It is made of nothing but the field itself.